Okay, so all right, so let's begin with the exercise problem. As we discussed, let's do the first problem first, and then I will go with the demonstration of the codes, and then we'll come back and solve the last two questions. So in the first question, it's a maximization problem, and we have a boolean, a string with boolean variable. So here it's a cop or a cap. Okay, so you can, if you don't like these symbols, you can convert 0 to 1. So one of them you choose as 0, the other symbol you choose as 1, and you can rewrite them as 0, 1 strings. But basically, I have given you this to say that it need not be always 0, 1. It can be yes, no. It could be two different options, like we see in circle and a square. So it could be anything that you have. So this is a combination of 6 such things. So if you say the cup is 0 and the cap is 1, you can just write the same way. But the first combination of 6 of these gives you a fitness of 15. The second one gives you 5, and so on and so forth. And we are trying to find the combination that will maximize the fitness value. Okay, so that's the problem. Now, there is a crossover probability of 0.8, mutation of 0.1. Now, we are going to be using schema theorem, which we talked about this morning, and find out how many strings would this particular schema that I have mentioned here would be produced after one iteration of GAs with the roulette wheel selection, which is the proportionate selection. So the formula takes care of that. Single point crossover and bitwise mutation. So all these operators are used to derive that formula that I gave you. So you need to look at that inequality formula, and also the example problem I had where I showed you how to use that, right? First you do that, and then we'll come back and look at the last part of the question. So let us see if you can do that. So first look at the schema theorem equation or inequation that we have there. Write it down on top, and then look at one by one what you have to do. So exercise 5, question 1. Okay. So the formula, if you look at, is mht plus 1 is greater than equal to mht times fh over f bar 1 minus pc delta h over L minus 1 minus pm of order h. So now we need to identify each one of the terms on the right hand side. Okay, so what is the h? Is this. So first let's find out what is mht. T is the current generation. So at this current population that's given, that's the generation at t. At generation t we have the population. How many copies does this schema represent? How many number? What is the number? All 6? All 6 represent this?
3 only.
3 only. Which are the 3?
First, third, and last.
First, third, and last. Everyone sees that? Why not second? Second, the first one is different. Okay, why not fourth? The third, the fourth one is different, is it not? Yeah. Well, no, the fourth one, yeah, fourth one is, well, the first one is different for the fourth. So likewise, you can see that only first, third, and the last one are represented by this schema. Everyone sees that? Okay. So now, what is this value then, mht?
3.
How many copies? 3 copies. 3 copies it has in the initial population, in this population t, at generation t. Any question, doubt? 3 is just the number of strings that this schema represents in the current population. The first position you have an intersection, and the fourth position you have a union. How many strings are there with this combination? That's the number 3, right? Okay, next is how do you compute FH? Average fitness. Average fitness of all those strings that this schema represents. So you identified the 3. So what's the average? 15 plus 14
13.
plus 12, 10 by 3. 13? Okay, that's FH. What is F bar? How do you compute F bar?
All of the
Entire population. Compute the entire population average.
9.8.
9.82. Okay. Then we've done up to here. Then PC is already given. Let's put it here. PC is given to be 0.8 and PM is given to be 0.1. So we now need delta H for that schema. How will you find it? So the position of this is 1. The first position is 1 and this position is 4. So 4 minus 1 because it's 1, 2, 3, 4. Okay. So 4 minus 1 or 3. Is that clear? It doesn't matter which way you look at. It's the difference I'm taking. But usually we say first gene, second gene, third gene, fourth gene. But you can also count this way: 1, 2, 3, 4, 5, 6. So 6 minus 3. Sorry, yeah, 6 minus 3 will be 3. So either way you do it, you will get the difference will be the same, right? Okay. And then order OH. How many fixed positions? 2. 1, 2. 2 fixed position. Okay, now you have everything, plug everything in, and you will get a right hand side value. So when you plug in, tell me what you are getting here.
So 1.269.
6 minus 1. 1 second. How much is this?
1.269.
Okay. So how many copies are you expecting? 2. 2 or more. It can be, because it says greater than this means it can be. It cannot be 1. That's why I said it can be more than. So MHT plus 1 can be greater than equal to 2. Right? I think our watch is about 10 minutes slow running every day. So you may try to switch it on 10 minutes fast. Okay. Everybody is fine with this result? Okay, so that was simple, right? Well, but this gives you some idea of how many copies it's going to get, and so main idea is for you to simulate. Now, if you want, what you could do at home, you can actually now do a selection, proportional selection, like the way we discussed, and crossover and mutation you can try simulate, and you see how many copies you are getting. So you may have to do few times to get this average idea of how much you'll be getting, but it'll be definitely more than 1.269 because there's some additive part which we have not added in this equation. Now to answer the next part, which of the two schemata, now there are two different schemata I'm saying, and one is complement to the other, right, is likely to take over the population in a GA run with the above parameter settings, and give reasons. Why? Yeah, because it's the same schema. So this part in the square bracket is entirely dependent on the schema, right? The L is fixed for both of them. So only thing that depends on, so this will be exactly the same for both these schema of the same order. So only way it will differ is MHT and FH. So this product, F bar is also doesn't depend on the schema. So whichever has this product bigger is going to have more copies in the next generation. So all you have to do is for each of them compute what is MHT times FH. So do that and let me know. So how many copies of each schema is there in the population? That's MHT. And then what's its fitness?
So first one will dominate. Intersection matters.
First one will dominate because it has the MHT is same for both. Each one of them has 3 copies each. So then it depends on whichever has a better fitness. And the first one is the average of the 3 highest values, right? And the other one is low. So clearly the first one is going to win. Okay? So you can make such comparisons, look into its own, what we call is the partition, own partition. There will be competitors and you can figure out which one is going to win. And then you get an idea that which way the GA is going to go. Okay? All right. Now we will try to look at the GA code. And first we're going to look at the binary coded GA to solve this problem, which we have seen before, and by now you know the optimal solution of this 3, 2, right? Because it's the solution of these 2 equations. If you put this equal to 0, put this bracket inside part equal to 0, you get 3, 2. Here are all the population size and everything is given. And first let's do that. Run 10 times and present the smallest, median, and worst F star value obtained. Somehow I have to give you this code, but do you have access to MATLAB over here? All of you? Some of you are outside students, you don't have your laptop here, right? So, but there will be a computer session. I tried to move it for tomorrow, but I haven't heard any email whether it's available. I will check today. Otherwise, I think for 7th it is booked. I think today was also it was booked, I think. Yeah, so if you want, we can go down, but we needed to solve those. But let me give the demonstration today, okay? So, but later on you can use this to do all this study. Those of you who have a laptop at home, we will try to upload it, the code somewhere. If not here, I'll put it on my website so you can download it, and then you can go to MATLAB and run them. I'll show you how to do it, okay? So let's go to the GA code. So we're talking about binary coded GA first, okay? So I have already moved to my MATLAB account here, okay? Not here, on my computer. And then GA.m is the main code. Here I don't get the screen with too much space here, but let me just try to first see this and so that I have a little more. So it's a code in MATLAB. Why does it go that way? Okay, maybe I do this. Okay, so it uses some population size, crossover probability. You can change this. So I think I said let's use 20, right? 0.9. Let's go back and see how much are those things, because I have it here, so I can look at it. 20, and tournament selection is already coded. Single point crossover, mutation, crossover probability 0.9, mutation probability 0. So first let's use 0 here. 0. Okay, and default accuracy, remember what is that? Now in this code, every variable has to have the same default accuracy. We didn't make it generic, so every variable you can give a different one. So we want 4 decimal places of accuracy. If you want less, we can just reduce. Let's say we do, how much did we say? Yeah, 4 decimal places. So once you give the accuracy, the code will automatically compute how much how many bits are needed. Here is the minimum dimension for every variable, 0, maximum 6, 0 to 6. Number of generations, we are going to run 50 generations, and dimension 2. Okay, I said 0 to 5, so let's do 0 to 5 here. Let's go by that. 0 to 5, 0 to 5. So 50 generations, 20 population size, 2 dimensions, 2 variables, and it's a minimization problem. So maximization variable should be put at -1. If you are maximizing, then you have to put it 1. Okay, and the code automatically does. See, this is how it computes the bit length and all that, which you have done as well. Then it decodes population and goes into this generation, selection, crossover, mutation, one by one, like we discussed. Now each one of them is written up again as a code. Then you evaluate, and then you update, and then you go into this loop, and then eventually you print out the result. Okay. If you have to change the objective function, this is where you have to go, evaluate.m, and here is the function written. So you don't touch anything up. Here you can put your function. So member 1 is x1, member 2 is x2. You can make it short by redefining member 1, member 2, say x1, x bracket 1 and x bracket 2, and then you write the function. So this is the minus 11 square and this is minus 7 square, and basically we have sending the function value. This one is for unconstrained. So if you have to handle constraint, you have to add it like a penalty for the binary coded GA. We stopped developing the binary coded GA for a long time after the real coded GAs were developed, and you will see the difference in the performance. So this is a very old code that I still show you because we talk about first the binary coded GA. So you see how it works, and then we move to RGA. Okay, so once you are happy with this, the objective function and everything, parameter setting, you go and simply run. Okay, so it's running already, but I need to move it up to C. So let me run again to show you what's happening. So you'll see that the command window place will get changed. So this is the new solution. Remember what was the result there? 3, 2, right? 3 and 2, and this function value should be 0. I haven't quite converged. Okay, look at if I run it again, 3.2.8. This is not very good. This one is close, but not. Look at the function value, it should be 0. So these are not very good solutions. Okay, but it's getting there. I need to run longer. So let's say, so this is the first run where it's supposed to be like this. Okay, now we are going to change few things. This says change the mutation probability now. Okay, so let me go and change few things. Where this is put right in the top here. Mutation probability says 0.5, which is a random search. Okay, so let's run it. Let me put it up. I can save it first and then move it up and run it. Okay, is it better than before? Yeah, even with 0.5, the mutation is changing a lot of things, but still it's working pretty well. You see. Now let's say we go to change the mutation probability to what it should be. So the size here, the two string length is 16 and 16 with 0.004. So bit length will be total 32. So the ideal way to set it, as I said, it's going to be to 1 by the string length. So what I'm going to do, probability of mutation, I'm going to change to 1.0 by 32.0. Okay, so that it's the right mutation probability that we would like to have. And let's run it. Okay, you have to run it few times to see what's happening. It's quite good. If you do now crossover probability down to, okay, let me increase the population size a little bit to see a little better effect. Let's say I double it, 40. Okay, and let me rerun this. You should expect a little better result. I mean, look at the function value, 0.04, supposed to be 0, right? Pretty close. This one is not so good. Once in a while you get, okay, this one is also not so good, but this one is pretty good, 0.009, 0.1. Okay, so population size definitely helps. Let's try to go and change this to 0.1, which I don't recommend, but I just want to see the effect, right? So let's run it. You see it's deteriorated. Now the values are 1 range, right? 1.2, 1.0. This one, after so many runs, we got 1 good. Okay, this one is not too bad also, not too bad, but this one is very bad. Like that. So it's 0.1 is not very good. Okay, you should use large crossover probability. Population size 100. So let's see 100 and get back to 0.9 here. Okay, and then let's try. Okay, this one is good. Okay, doesn't seem to matter that much, but seems to have that some of the runs come very close. Okay, so maybe 50 generation is not very much. So let's try to go to maybe, let's say, take a large number, 200. Okay, and let's try now. 0.06, 0.04, 0.6, 0.03, 0.122. Okay, the values are quite good now, and here I want a bit more, much better than, because I'm spending so much generation, it should have been more. But this is how the binary GAs is when you are solving a real coded problem with binary GA. Okay? So you can try this yourself, experiment, and get some ideas of what's happening. But let me now move to RGA. Okay, this is the real coded GA we talked about today. So you got a rough idea, right, of how much, what's the performance like here. So RGA is a different code now. It's also in MATLAB. Now here you have to do things a little differently, not in the main code. Main code, the way we've done it, you don't have to do anything in the main code. You go to the truefunc.m. That's where you define your problem. So here we made it in shorthand because this is the code we use more often than the binary coded GA. We put it different problems you can put under different cases. So all your problems are there. Anytime you want to run them, you can. So you can, new problem, you can just add after case, I think I have up to case 4, you can just add case 5 over here and put your function. Okay? Here is the one we are trying to solve. And this is case 1. All right? This is case 1. So somewhere you have to say that, case 1, I think it's done in setparam.m. Go up. This is problem 1. That is the case 1. When you say problem equal to 1 means it knows that it has to use the first problem specified under truefunc.m. And for the first problem, there are 2 variables. Here the k is the number of variables. It says here number of constraint is 0. We'll go from 0 to 5, 0 to 5 like we did in the case of binary coded GA. So these are, you have to set for your problem what is the lower bound, upper bound. Here there is no binary string, so you don't have to say precision. It can get arbitrary precision, right? And then, so only specify how many variables, number of constraints, and lower and upper bound of variables. The population size and all that are set here at the end of this code. So 10 times the number of variables, so you use 20. Okay, the number of generations 50. Crossover probability 0.9. Mutation probability is 1 over the number of variables. I said that we usually use. Eta C is the SPX eta, right? That's, I said we use usually 2. Mutation, anything from 10 to 50. Sometimes you use 100 as well. So more the number you use, the better precision you would get. So we use 20, say here. Okay. Let's first run this and see what happens. So everything is set up already. I have to go to rga.m. and let's see, to move it up to see what results are coming. I'm going to run it. Change folder because it's in a different directory. Okay, here it gives the details of every generation, what is the value and everything. So generation number 38, 39, the best individual, the fitness. Look at the fitness we got at the end after 50 generations. Okay, 0.0006. We never got it with binary coded GA, right? That much precision. And 3.00 up to 2 decimal places we got the optima. 1.99 again up to 2 decimal we got it, right? So it's only with 20 population size, not even 40, that we had to use in binary coded GA, and running only up to 50 generations. Okay, we can run it again just to see what happens. Look at -7. Okay, 3.001, 1.999. So it's a pretty good difference, as you can see, between binary coded GA and real coded GA. So all the stuff I said in the morning makes sense now, right? Unless I show you some results, you may still think what's going on. But all these calculation of this bimodal distribution, giving stress on solutions close to the parents, the way we do it here, everything works together in a harmony, okay, when you're doing this. So that's why we use this algorithm more often than the binary coded GA for solving real parameter problem. Binary coded GA is still useful, as I said, when you have a mixed integer. So some of the variables you have to code in binary strings, like the material and all that. We will borrow its crossover and all that and put it with this and do it. Okay, so this is the, now when I give you the code, you can then try the effects of changing the eta c from 2 to maybe, you can try that. Let's go to setparam m, and I go and change 2 to let's say 50. Just take a very bad value here, and let us see what happens. It'll still not be that bad, I suppose. You have to save it. We go to rga.m and we run it. Not too bad still. So it's not that sensitive, right? You see, I have used 50. Still it is not too bad, but it's not as good as eta equal to 2. And it's a 2 variable problem. It will show up when you go to higher dimensions and all that. You want to change any other parameter? We can change. Let me get back to 2. This is another one. Maybe if you use 0.1, for example, crossover. This is the crossover probability. 0.1. Let's save it and go to the rga.m and run it. Let's see what happens. Yeah, still not too bad. So it's a pretty good algorithm to fool, actually. Okay, so it's not that sensitive to these values. It works under large parameter settings. But if you want to get the best performance, then you have to do those things that I mentioned to you, right? 0.9 here, and I think the rest of the things are fine. Okay, so this question 3 in exercise 5. There are few parameter settings that I want you to do. You can try that. Okay, number 4. Okay, that's still a okay. So all these are okay. We'll create something out of it. Let me see what we have done here. Yeah, maybe we can do one of that. Okay, so let me still demonstrate to you the 4th problem, which is a constraint problem. So the constraint problem, if you look at on page 174, we have the same objective function, but there are 2 constraints I have added. So we have coded that already here. I think it's under this case number 3. What is case number 4? 4 is different. Okay, case number 3. Here is my objective function. Here are 2 constraints. The constraints have to be put as greater than equal to 0. Okay, and see, I've normalized. I've divided by the constant value 26, and this one is 20, and both of them have to be greater than equal to 0. This is how the code takes it. Okay, and so this does not require any penalty parameter or anything. So all I have to do now is go to set param and set this to be problem 3 instead of 1. So I'll just set this to problem 3 because this is already coded in my true func, and set param, I just have to say which problem I'm going to take. Same code, everything else is the same. You can go to set param when it's case 3, you can see what's happening. This is for constraint handling. Still there are 2 variables. Number of constraints are now 2, and then minimum maximum is 0 to 5, 0 to 5 for both variables. No parameter is needed for penalty parameter or anything else. What else I wanted to tell you? Okay, the variable bounds, because it says 0 to 5, 0 to 5, but those are not constraints in GA, right? We always restrict our search within 0 to 5. The SBX is modified to not create anything outside. So 0 to 5, 0 to 5 already takes care of it. And here I've got the parameter setting. So it will be still 20, 50 generations, 0.9, 1 by 2, 0.5 mutation probability, 2 and 20. Okay, so let's see what happens. We go and run it. Okay, where does the optima go for this? This is still greater than equal to. So if I put 0, 0, it's infeasible. So now the optima is moved to 0.8 or something. Then the function value goes to about 60, right? Is that the case? Yeah, that's the case. Okay, so let's see now if I run it, what happens. Okay, see, 60.387, right? And the optima is moved to this. Okay. Now, if you see when I'm getting this result, so this is generation 50 already, because I asked it to run up to that point. Now look at 49, very similar, 48, 47. Just keep an attention on this 60.3887 because that's the function value. We could actually go all the way up. Okay, it just changed. So up at 30th generation, it found that solution. After that, it couldn't find anything better. So most likely, that's really the optimum. Okay, so we could have terminated after 30th generation if we had kept a check that if last 5 generations I didn't have an improvement by more than, let's say, 1% or something, then you quit. I could have terminated at 35 generations instead of going to 50 generations. But this code is terminating based on how many generations you ask it to go. Okay, so that could be either too much or too little. So keeping such a dynamic check is a good idea. All right, so that's that. You can run it again. We can see what happens. We got slightly different result, but again at the same area. Run it again, slightly different, same area. So it may not be happening at first decimal or second decimal places. If you want more precise results, you have to then increase your generation. So we have to maybe make this 20 times to make it 40, and maybe run it a little longer, let's say 100 generation. So I'm giving it more time to have it more reliable results. Then go to rga.m and run it. 60.39, let's run it again. 60.3754, 3783. Now at least up to 1 decimal we have the same result, right? Yeah, so they're close. So population size, when you increase overruns, you get not much variation, okay? But it's a stochastic algorithm, so you'll never get the same result. Or I shouldn't say never, but most cases you'll not get the same result. So usually what we do, we make 10 runs and note down everything, and then we report the best result we've got, the median result we've got, and the worst result we've got. That way, to the reader, it gives an idea that out of 10 runs, all of them seem to have come at the same place. Right? Any question? No? Okay. Let's do the second part of that. Actually, I have solved the fifth problem now. Fifth problem. Okay. So now we'll be doing the fourth one, where I will show you. Yeah, question? There was?
Sir, that mutation index, what is it means for mutation?
Eta m. So that polynomial for mutation, I told you, it also has a polynomial of degree what? So eta m is the polynomial degree for the mutation operator. So usually we keep 20 plus, so 20 to 100. Okay, so here we kept 20. We can increase it a bit more. Okay, now for the fourth problem, actually, I asked you to do with the bracket operator, not with the penalty parameterless constraint handling. This one is results with penalty parameterless constraint handling. Now let's get back to the true function, and I think I have the second case as that. Second case is constraint problem as unconstrained approach by penalty. So here is the function again. Here are the constraints. Is that in greater than equal to form? Yeah, greater than equal to form, both of them. And now I ask you to supply supply a penalty parameter value. So R value. So let's say we used 1 million. How much do you say? First we use 10 to the power 0 or 1. Okay. Then see how I'm doing it. CV, my constraint violation is 0. And then for two constraints that I have, if it is negative, which means the constraint will be violated, then I'm taking the absolute of that and adding to CV. So I'm not squaring it, I'm just adding it. And then after the CV is computed, this is how I get the penalized function, f plus r times CV. Okay? R I can choose. I have chosen r equal to 1 here. All right. So I save it because I changed the penalty parameter. Set parameter. I have to now, first thing I have to do is go and change the problem to 2 because the case 2, which is coded already. And now I'm going to see what is case 2. So 2 variables, no constraint. Why I'm saying no constraint? Because I've converted the constraint into unconstrained problem. So to my final function is an unconstrained function. So that's why I'm saying no constraint here. Although it has constraints, but I've converted it into unconstrained problem by penalty approach. 0505. Okay. Then I come here. Let's keep with 20. Let's see what happens. 100 generations, 0.9, 1 by k2. These are standard stuff. Okay. So let's save this one and go and run this. Okay. Why is it coming to 2.99 and 2.0? It's supposed to be 0.8, right? So just to tell you what had happened here in this problem, if you recall, it was sort of like this, right? But then goes like this, and then here was a constraint, and it said this side is feasible, and here is another constraint that says this side is feasible. So where does the optima go? This is at 3, 2. The optima actually goes here, right? 0.89 and something was there, 1 point something, right? But now what result I've got is almost 3,2. Why? R is said to be what here? 1. So when you set R equal to 1, then you have F plus 1 times CV x, which is the constraint violation. The constraint violation effect is very less. So this optima has not moved much, and that's what it has found. Okay, so now I can try with other values. Okay, so go to truefunc, and instead of 1, next is use 1000. But let me slowly increase. Let's make it 10. Okay, save it. And I'm not going to change any other parameter there. Same GA parameter, I run it. Remember, this is 2.99, 2.0, and the value is 0.6914. Where did it go? 6.83. Now 2.95, 2.0, slightly moved towards it. It's somewhere here now. So value is 6 point. Just to see whether that's the value, you have to run it few times. Every time we seem to be getting there, right? Close to it. So that means that is really the minima. It's not 3.2 anymore with the function value 0, but it has moved to a function value of about 6.84. Okay, here, that is the function value, and these are the solutions. When you put R equal to 10. So if you look at this, R equal to 1, what did we have? Around 0.69 or something, 0.68. I'm talking about function value. And R, when I made R equal to 1, this was the value. Now it is 6.84 when I put R equal to 10. I'm going to now do R equal to 100. Okay, go to truefunc, 100. Save, come to rga.m and run. Okay, we are getting 59.5668. Run it again. 59.5668. Run it again. Wow, it's every time getting the same thing. 59.5668. Already moved. So, and the value f x1, x2 is 2.4, 2.643. So came somewhere here. Now let's do one more time. 1000. And we save it, and we go to rga.m and run. And now we are getting very close to the optima, right? So this is 60.392. Remember, this is what we had when we did the penalty parameterless approach. But that was just one run without any penalty parameter. Here, to get to this, we had to have a good idea of what is R. Okay, so after some R, so looks like somewhere around 100 to 1000, if you choose a R, from there on it'll start to work. Okay, so that's the thing you have to know for a new problem, because it's not really, so there is a bit of experimentation that's needed if you want to deal with penalty parameter approach. Let's try one more 0. So we do 10,000. What happens? So we save, we go to RGA, run. 60.3775, 3838, doesn't seem to be changing, right? Yeah, so it's staying there somewhat, 60.38. So no matter what you use after that, it's not going to change the optima. So best to use a large value. Now I told you that with the classical approach, because it's used gradients, there are issues to deal with large values, because when you use R equal to 1 million, the F value is really not emphasized well. Let's try to use one and see what happens here, whether GA gets affected or not. So I'm going to use E7, let's say. Sorry, where did I put that? E7 here. So it's 10 million I'm using now R. Okay, 10 times e to the 10 to the power 7 is what I'm using. Save it. rga.m. I'm going to run. It's not crashing. It's working and still giving me a good result, right? Why? So why is it that this is not an issue with GA? When I put a large R here, Okay, even 10 to the power 10 million I put here, and these function values are in the range of 60. Still works, and I have not used the penalty parameterless approach. This is still penalized function. I'm still minimizing this.
It doesn't go in that direction once it goes. If it goes like I don't know, a little bit above, it won't go up beyond that. It will just come back.
Right. So first thing is we are not using any gradient anywhere. Okay. So this function, can we get back to the paper here? So here the function values are normal. Here they are from 60 to whatever, 200, 300, let's say. Here the function values. Here, when I multiplied by 10 million, every one of them has a constraint violation. If you have a constraint violation of 1 unit, your function value is 10 million plus the function value there. So let's say in the order of 10 million. So here your function values are the order of 10 million in this region. Here they are 60 to 100, 200, okay? But I'm using no gradient. So I'm starting with a random population 0 to 5. 5 is somewhere here, and 0 to 5 maybe somewhere here. So this is my range. So these are all infeasible. So only feasible part is this. This is the only feasible part. Okay. Rest all are infeasible. So rest all are in the range of 10 million or more. Okay. So if you visualize now the function, can you visualize in 3D? This part, there is a small slope going up because minimum is still this point. So small slope going up. Here, from after this line onwards, suddenly the function value shoots up to 10 million. So suddenly shoots up, but then that side is small slope. Now I'm using GA. That means I'm starting with lots of points. Okay. Each of them I need a function value, and that is this f plus 10 million times constraint violation. On this side, I've got 10 million value. On that side, if I've got a point, if I'm lucky, I have a value of 60, 70 like that. So where is the problem? If I'm doing selection operation, I'm comparing these two, which one will get selected? I'm minimizing. So this side will get selected. If I do 2 from here, infeasible side, this is maybe 10 million and this may be 2 times 10 million. So 1 times 10 million is better. Again, that works. Anytime I'm taking one infeasible, one feasible, it's just the difference is large, but it still tells me this is better. I am not interested in how much is the difference, and I'm not doing anything with that. I just want to know, is it better? Like when I have 2 individuals, I'm comparing the 2 and the smaller one I'm keeping. I don't care how much smaller it is. Okay? As long as one is smaller, even if it's 0.001 smaller, it is still smaller. So GA doesn't really care about how much small. So no matter how much large you keep your R, it's not a problem. As long as you take it to maybe 10 to the power 100, where now GA will have overflow error for computing the function value. That's a different issue. But algorithmically, there is no issue. So you can take any large R. You don't need to do it in sequence. You will get there wherever you want to be. See the differences I'm talking about? Okay. Now the issues are still there, of course, if you have many, many constraints. Since I'm normalizing, adding them as one constraint violation, that can create some artificial local minima and stuff like that. Those issues with penalty function is still there. But the numerical issues that I talked to you about, for the penalty function approach to work, we need to have a sequential way of doing it. We don't need it here. Okay. Then the question you may ask is, when you did small r, why didn't it work? Okay. After certain large r, some value of r critical, anything will work, will give you the optima like I showed you, right? Now, anything below that critical, why doesn't it give me the optima? No, that's not the reason. Yeah, so why doesn't it go there? Right. When I take r equal to 1, if I show you the function value, the minima is right here. When I say r equal to 10, it moved a little bit here. R equal to thing. So it's the minima of this function now we are finding, not the constraint problem minima. I'm finding the minima of this composite function, fx plus this. Wherever is the minima, it will find it. Now when you choose small r, the minima doesn't reach the constraint minima, right? But as soon as you have a large r that reached that, the critical r that reached that, anything beyond that, you don't have to worry. But if you're small, then that critical, then you will not reach there. It will be still infeasible. So that's not the problem with GA. It's the problem with your function and choice of R. You see, you have to be understanding what's going on, right? So know that for a problem, in order for the penalty function to work, you need a critical R, beyond which you can give anything. But if you use a classical point-by-point method, you can't give any large R because of the issue of gradient computation and all this. But here I show you it's not a matter. So if you are using GA type of code like this here, RGA, and you have a constraint problem, you can close your eye and use 1 million R, because you may think, oh, the critical R will be always less than 1 million, so I'm safe. That's one way to do, and that's how we solve constraint problems. One of the ways to solve constraint problems. But it still needs that R. You still may be wrong. 1 million still may be less for another problem. Okay, so then you have to try one more time, increasing it higher value and see what happens. But the penalty parameterless approach, which I showed you before this, I didn't even ask you any penalty parameter, and we still get the same result, which means it doesn't require anything. Okay, so you don't have to worry about choosing an R. So that's a bit better. So number 5 here question is the best way to solve, and I would recommend you to use that method instead of this penalty approach. Is that clear?
Sir, in the penalty approach, can you go to the first one to assign the R value, the sig parameter that part of the code?
You want to see? Here I'm not setting R. R I am setting in the true func. Here only the parameter values I'm choosing. Lower bound, upper bound for 2 variables. No constraint, 2 variables I have in the problem. True func, you need to provide the penalty parameter.
Okay, that is R value.
R value. Then I am actually computing the constraint violation, because for a solution both constraints need not be violated. So I find out if any constraint is violated, I add a penalty. I compute how much is the violation, and then I am multiplying with penalty parameter, that constraint violation, adding to F,
Sir,
and sending that as F.
So in that problem, if there is a third constant, then that I would be 1 to 3.
This will be thrown to 3. This is the number of constraints, right? I should have made it more generic. This is hard-coded. Well, these are the cases. So because it's case only for this problem, you can hard-code it inside. For your new problem, you have to go and write another case. Okay?
And sir, CV denotes what, sir?
Constraint violation. So I'm checking that if any of the constraint value is negative, which means my constraint is violated. Because my constraint should be greater than or equal to 0. That's how I have put here. Every one of them should be greater than or equal to 0. If it is less than 0, that means it's violated. And then I take the absolute value and call it the CV. And I'm
GI is less than 0, that denotes that thing, sir, that if the constraint is violated.
yes. If this happens for a particular x, then this constraint, the ith constraint, is violated. Okay? Any other question? Okay, so this code you can hard code like this for constraint violation, but I would not recommend, as I said, because it still requires you to supply this penalty parameter. Why stay in that dilemma, how much to put? Rather, you come as constant 3, and here you just supply the objective function and constraints and nothing more. Okay, make sure these are all normalized and greater than or equal to form. And then the code takes care of, when I have the tournament selection, code is there, it takes care of what to do. Those kinds of things we said, that if one is feasible, the other is infeasible. Feasible wins. Too feasible, the one with constraint violation wins. And so basically, if you look at the code at the end here, this part takes care of it. So it's actually checking if the number of constraints is greater than 0, then it checks the GI value. Okay, and it also computes the constraint violation, and it's actually sending now 2 things instead of 1 thing. It's sending the function value and also the constraint violation. This is the same as CV. It's sending it. So now the selection operator for every solution has these 2 values, function value and constraint violation, separated, not added together. So it first checks whether this is 0 for both solutions you are comparing or not. If this is both of them 0, then it sees which one has a smaller f. That one wins. If both one is 0, constraint violation 0, the other is non-zero, it automatically sends the 0th one, the constraint violation 0. That means the feasible one.
Cases are
If both are violated, then it says which one has the smallest violation. It doesn't even check the F. So all these are coded in selection.m or whatever code is there for the selection operator. So those are all hard-coded because that's the algorithm. This one is just supplying all these values, and then it takes care of it. Okay. All right. So looks like there was no home assignment the manual work for that. If you have no further question, then we'll move to exercise 7, which we're supposed to do today. Let's do the first problem. I will arrange to give you both these codes and also another code called nsga2.m, okay, so which is for multi-objective. We'll figure out a way to get to you. Okay, now let's see exercise problem 7. Okay. All right. So I want to plus it and then do it this way. Oh, that I don't like. So we'll just do this way. Okay. So this is the 7th exercise. We'll try to do the first one. Okay. So what is the first one? Mutation operator. Although I have not talked about 1 plus 1, yes, but let's say I showed you. Okay, let me take 1 minute to just tell you what I showed you before, and then we can do this. So for mutation, if this is my variable x, and I'm currently, let's say this is lower bound, this is upper bound, and my current point is here, x. I want to mutate it. That means I want to just perturb it in its neighborhood. I get another value in the neighborhood with a probability distribution. I told you normal distribution is one that we commonly use. This can be another distribution. This is not normal, but it has such a distribution. It has such a distribution with the max or mean being at 0. Okay, this distribution, as you see, a over sigma square plus x square. So so this is of course mutated at x equal to 0. So let me just think a little bit here. Yeah, so yeah, this is mutated at x equal to, this location is at x, is at the, so at this point you are putting this, right? At this point you are putting this, and then you get this distribution. So sigma is supposed to be given to you. A is something you need to find. So first thing is, in order for this to be a probability distribution, so this is, let's say I want to write it as a probability distribution for a given sigma, what should be the value of A? So if I tell you this is a probability distribution, what is the property that probability distribution should have? Area under all possible x, that means cumulative probability should be 1. That's why I've given here also a hint. So this one can go to x equal to minus infinity to x equal to plus infinity. So you need to basically integrate this function from minus infinity to plus infinity, a over sigma square plus x square dx should be equal to 1. Can you solve this to find a? So what is the integration of this function? Tan inverse x by sigma, and there will be a here. A constant will be there. And divide by? Okay. This you can see from standard book if you are a little confused. Then say minus infinity to plus infinity. That should be equal to 1. So let's put plus infinity to this. What happens? So a by sigma can come out. When I put infinity here, what happens? Pi by 2 minus, when I put minus infinity, minus pi by 2. That should be equal to 1. So that means a over sigma times pi equal to, this is pi by 2 plus pi by 2, pi equal to 1. That means what is a? Sigma by pi. So this is what I get if this has to be a probability distribution. So that means my probability distribution for a given sigma is sigma by pi over sigma square plus x square. Okay. So now I got the probability distribution. Now the question is, I am using a random number of 0.723. So u I have used as 0.723. It should be between 0 and 1 to create a child. Okay, I am using this distribution with this probability where x is given to be 10, x is given to be 10 here, so this is the location, and sigma is given to be 2, so sigma is 2. Okay, so what would be the mutated child? So all this distribution is actually, this distribution, I shouldn't have written 10 here, this distribution is based on 0, as I said. This distribution has to be on 0. So let's first mutate as if the parent is at 0th location, and whatever is the perturbation we are going to add to 10, and then we are going to get the mutated child. Okay, the question now is this. Let's say I've got a probability distribution that looks like this on x. So this goes from some value to some value, and these are only positive probabilities that we have. We know that as soon as a probability distribution, the area here is 1. Right? This is what exactly we've done, that if you put it this way, then the area under the curve will be 1. Now, how do I use this to create a point based on this probability distribution? Does anyone know? I know the probability distribution. Now, if I ask you now this question, can you create a point based on this probability distribution? How will you create? Create a random point using this probability distribution. So first thing you need, yeah, go ahead.
X equal to that value and
No, first thing you have to ask me, what is the random number? Okay, the way the idea goes is this. So random number can go between 0 to 1. If I give you a value 0 for the random, this is one of the extreme, what point would you tell me? This will be always this extreme. So this is for u equal to 0. U equal to 1, you will give me this point. You will never give me anything here and here because the probability is 0. It will never be created like that. Okay, that's all information you have. Now if I give you u equal to 0.23, how will you create that point? It will be somewhere in between. But where is that?
Minus infinity to that point.
No, there's no minus infinity. It goes from 0 to, it goes to, let's say, a to b. This could be minus infinity. This could be plus. But you cannot generalize and say always minus infinity, plus infinity. What area?
deviation from A to whatever.
A to whatever. That's what I'm trying to find. So if it is this point, let's say call this maybe y, then this area should be what? 0.23. Should be u. Should be your random number. Let's see if this idea works. I told you u equal to 0. So where does the area go? U is 0. So write A because you're not moving with any area. So that's the point. What if u equal to 1? That means you are looking for a point where the area will be 1. What is that point? Is this. So another name for doing this is cumulative probability. So this is called the PDF, probability distribution function. You can also draw now a cumulative distribution function. And it's a monotonic function. It starts at 0 at A and ends at 1 at B. So this is called the CDF, cumulative distribution function. So that means the way it's calculated is the integration. At this point, this value is actually u. This value is actually u. This is the integration of this area. It's put there as u. So if you know the CDF, then for any random number which is here, so this is going to 0 to 1, 0 here. So any random number that you have, all you have to do is get there and get the corresponding value, because this is monotonically increasing, so you'll always have one value that will give you that. But we may not use the CDF concept, we can just integrate and do it. So then can you relate u and y now? Let's say this probability is p as a function of x. Then can you tell me how u, p and y related? U, which was this area, y is this point, and px is the probability function that we had. How are they related? You already told me, right? The area. So what is that area? From A, x equal to A to x equal to y, I have to integrate the probability. Dx should be what? U. This is the thing you have to remember. So knowing the probability distribution and knowing the random number for which you will be creating the point and knowing the lower bound, you can solve this equation and find what should be y. So this from here, find y. That's it. Can you now solve this problem? I gave you the probability function. Sorry, this is the function. I gave you the probability function. Px is known. Ignore the sigma for a given sigma. Sigma is given to be 2. So wherever there is sigma, you can put 2. Okay? And the u is given 0.723. Can you tell me what should be y? What is a in this problem? What is a, capital A in this problem? What is the lower bound? Minus infinity. So a in this problem is because it starts from minus infinity. That's how we calculated this probability, right? So minus infinity is a. So can you find it now? A is minus infinity, px is this function, and u is given to be 0.723, and sigma is given to be 2. So find and tell me what is y. This is the whole concept of creating a point using probability function. You would need this in many, many different fields, okay, this concept. And the integration of this function is already given here, so you need that. Okay, now you can compute this. I don't have the result. How much? Point?
0.024.
You are also finding, two people are finding the same result? Okay, that means it must be correct.
So, what does this mean then? X sigma will 10, the sigma I got.
Okay, now we haven't done it yet. We haven't done it. Anything wrong? Acha, this one gone. I think I didn't touch it for a while. Sorry. Yeah, okay. So this is what we get if the x was at 0. Okay? So, but now x is at 10. So that means we have to add this to 10 to get the perturbation around 10. So x is the parent point. Is the 10 point is the parent value, right? We have to mutate around 10. So we got the perturbation we needed. So y now, the mutated child x dash, is going to be 10 plus y, 0.024 or 10.024. So it's a small perturbation. 10.024 is a small perturbation for 10, but that is how mutation operator creates a new point in the vicinity of the current point. Okay, using this distribution. If you use Gaussian, it will be something else. Now you can see the effect. If you had used some other u, it can be less than 10 as well, because if u is less than 0.5, it can go on the other side. It can be less than, this value will be negative. Okay, so around 10 you will have now these values. Okay, 1.68, that's what I thought will come, but they're saying 0.024. This has to be in radian, yeah. Yeah, so have you done the radian before you've done that? Okay, so this will be 1.68. And so this is 1.68. So this will be around 11.68, which makes sense to me, yeah. So 10 to 11.68 it goes to. That's the perturbation. That can also happen whatever you computed wrongly before, but maybe for a different random number. But if you do it many times, the distribution will actually follow this pattern. Okay, there will be more likely of points close to 10 and less likely as you go away. All right. So this is that effect that I wanted for you to calculate, because if you're writing a code on your own, you have to code all these. Okay, what mutation probability you are having and how to get this perturbation value added to the new one. All these are coded in our GA code. So when you have it, you will see, if you go to the respective file, you will see how these things are happening. Okay, any other question about the assignment? So you can submit us the first question of exercise 5, the first question, and the first question of exercise 7 as today's assignment. If you want to do it tomorrow, it's fine as well. Okay. All right. So I think we are finished a little early today. I don't want to start the lecture one more time, because I think one day that's enough. Except to say is that has it occurred to any of you this mutation that you're seeing, where I've been telling that this mutation is going to give you a perturb point in the vicinity of the current point? And when we did the crossover operator, then also we are getting children created in the vicinity of the parents. So what's the difference? This is a very common question I have. So let me rephrase the question. So if I had, can you save the paper here, please? So when we did the SBX, if this is my parent 1 P1, this is my parent 2 P2, I actually have, so that means these points are very likely to be created near the parents. When you do mutation, polynomial or whatever, I just need one point, P. I also, if I'm doing polynomial, I also actually have this kind of distribution. So here also I'm creating points near the parents. So what's the difference? Why am I doing both? Because they seem to be very similar. I mean, this operator in this example, we had a different probability distribution, maybe like this. But again, it's the same thing. This dashed one also keeping points close to the parent more often, creating points close to this P more often than away. But is there any fundamental difference, or do you really need both? It's a good question, right? First of all, it's a good question. So what's the difference? You need to understand the difference. In order to do this, I don't need any other parent. So somehow I have to supply the standard deviation. Somehow I need to fix the probability distribution. Like in this case, we fixed the probability in the mutation case. I have fixed this to be 2. Here sigma is actually the sort of like standard deviation. If you make it large, you will be making it, I think you will be making it, okay, I have to close it now. So what if this is large? How the distribution becomes? What if this is 16 or something? So you're dividing by a large number, so you're probably going to get more picky. It'll probably be like this. Okay? So it has an effect very similar to what we talked about here, but everything is controlled by this external parameter 4, or the sigma in this case. By choosing sigma, you are saying how much spread it should have. Are the points going to be very close to P, or they can be here as well? By controlling that number 4 or the sigma, you have to do that. That's an external number. You have to know how to set it. What's happening here? I showed you, right? When you have these 2 points, you have this distribution. So if I'm thinking of this point, it has a good probability. But if I now have 2 points that are here and here, 2 parents, P2, let's say P2 dash and P1 dash, if they are like this, how is this distribution will look like? They'll be very picky, like this, like I showed you, right? They are not going far away now. Now creating this point as a child of these 2 parents is almost unlikely. So it also is talking about the spread, but the spread of this now depends on the location of the 2 parents. Their difference, you are not supplying that externally. It depends on how your population diversity is. If your population is diverse, you can have some effect like this. It can be far away. If the population is very close to each other, you don't want to, you cannot go away rather, right? But mutation, whether the population is close or population is far away, you have to supply that 4 or sigma. Either you keep it fixed all along, or you vary it as you go along by some external means. So these are externally controlled. Totally depends on you how you're doing it. These ones are population driven. It's self-adaptive. So this is more self-adaptive. It can adapt itself, depend on what the population diversity is. This one is external. It's not self-adaptive. It is more of externally controlled. Okay? Externally controlled. You see the difference? Both are needed, because what if you have a population that is converged very close to each other at a wrong place because of whatever reason? Maybe you have a high selection pressure or anything. Wrong place. By the time it was going to the optima, the population diversity has reduced so much because of high selection pressure or whatever that it just couldn't go there, and it lost the diversity. Once it happened with the SBX, you can never regain. Well, unless the function information helps you to regain, it is not going to regain, right? But now if you have this kind of mutation with a fixed variance with 4 or some sigma, always this kind of perturbation is happening. With this particular standard deviation, perturbations are always happening. So if this is a wrong convergence, it will take you out quickly. If it's the right convergence, still it's trying to take away, right? Still it's trying to destroy your well-converged populations. That's the problem. Okay, but you don't know whether it's the right convergence or the wrong convergence. But fortunately, mutation is done with small probability. So to some of them, it is destroying when you have right convergence, but others are still there, and when you compute the function value, these ones are winning. The bad ones that's created by mutation will die off, so you don't have to worry. But if it was a wrong convergence, now the mutated childs are becoming important now, because they will have good values, fitness, and the old population will go away and the search will again start. So both have their own role. Okay, both can be detrimental, both can be useful, but when you put them together, if one is not functioning, other can help, and vice versa, right? But you should understand the need for them, because very easily you look at these plots and you can think they're doing the same thing. Why are you doing it twice? But one is self-controlled, okay, population diversity based control, which you have no control on it. Okay, you just have control with the eta c. But this one here, you are directly have to control the diversity, and both are important, both are needed. Is that clear? Okay, I think that's enough for the day. So tomorrow, let's just plan a little bit, because we have little time. So obviously, I'm not be able to finish the whole thing that I have laid down here. I will probably So there is little bit left today on the lecture 5 that I started today, which I'm going to finish next class. Let me see. I think I need to go to lectures. Okay. So lecture 5 we have started. I'm going to just finish it. It's going to take me maybe 15-20 minutes. Then lecture 6 was Dilip's things that you already have. Okay. Lecture 7, I'm going to give you the billion variable example. Okay, tomorrow. That is this example. It might take me half an hour to explain the whole thing, so because I want you to understand what it takes to solve such a large case problem and all kinds of knowledge we have used here. So that's very important for you to know the customization process. I'm going to briefly talk about multimodal, and probably not in this much detail. And bi-level I'm going to not do. This part, bi-level, multi-level stuff, I'm not going to do. Okay, tomorrow at least. So I'll skip all that. Okay, so that's, and I want to keep some time at least so I can start the L8, because this is supposed to be for tomorrow with the multi-criteria.